Alright, so this is the chemistry lesson video for chapter 17. I realized that I picked a terrible background color considering that the sun is starting to shine in my windows. So just bear with me, hopefully you can at least see the important stuff. So I'm cramming everything from chapter 17 into one video because we just need bits and pieces of the whole chapter. If you want a more in-depth look at chapter 17, then in my honors chemistry tab on my website, you can see fully what they learn in chapter 17. But for regular, we just need to kind of pick around and just get a little bit of different definitions and things like that. So in thermochemistry, we're going to talk about heat because thermo means heat and chemistry means reactions and physical processes where we have some changes going on. So heat is a form of energy that always flows from a warmer object to a cooler object, and heat is actually represented by a Q. I know that's kind of weird, but H is already taken. A lowercase h is Planck's constant, and uppercase h is enthalpy, which is related to heat, but heat itself is represented by the letter Q. So thermochemistry is concerned with the flow of heat between a chemical system, which is your reaction, and its surroundings. So a system is the specific part of the universe on which you focus your attention. So that would be your reaction. The surroundings are everything outside of the system. So if you have a reaction occurring in a beaker, the beaker is not part of the system. Just the chemicals that are actually reacting are part of the system. Everything else is surroundings. So the beaker surroundings, if you stick your hand in there, unless your hand becomes a part of the reaction, that's a surrounding. Sticking a thermometer in there, that's a surrounding, again, unless the thermometer starts becoming part of the reaction. And then the system and the surroundings together constitute the universe. So the important thing to remember is unless you are in the reaction yourself, you are a surrounding, because otherwise you get what I'm about to show you on the next slide backwards a lot. Because you want to be part of the system, but you're not. So in thermochemical calculations, the direction of heat flow is given from the point of view of the system. That's the reaction, so not you. It doesn't matter what you think is happening, it's what's happening in the system. So a process that absorbs heat from the surroundings is called an endothermic process. So you may think, well, if it's endothermic and it's absorbing heat, it must get hotter, so if I touch it, it's going to feel hot. Well, remember, it's not about your point of view. You're a surrounding. It's about the system's point of view. So the system is absorbing heat. Well, if you touch it, it's going to absorb heat from you because you are a surrounding. So if something takes heat away from you, it's going to feel cold when you touch it. Okay, and so see, that's where people get kind of tripped up. Like they understand, oh, endothermic absorbs heat. Heat goes in. That makes sense. But when you touch it, it's going to feel cold because it's pulling the heat from your hand. A process that loses heat to the surroundings is called exothermic. So heat is exiting the system. So again, you may think, oh, well, if it's exiting the system, it's going to feel cold when I touch it. But remember, you're not the system. You're the surroundings. So when you touch it, it's releasing heat into your hand. So to you, it is going to feel hot. All right? If you're in my class, I show you examples of both of these processes, and you can actually touch them and feel what's happening. But since this is just an online video, you clearly can't touch anything. So, you know, oh well. Alright, so let's go into some calculations. If you took physical science, you remember this formula, Q equals mc delta T. So heat, which is Q, equals mc times delta T. So m is mass, C is specific heat capacity, or just called specific heat, and delta T is change in temperature. Capital delta, which is just a triangle, means change in science, just like it does in math when you learn slope. Mass is going to be in grams. Specific heat has kind of weird units. It's joules per grams times degrees Celsius, and that's, of course, just to cancel out units. And change in temperature is in degrees Celsius. So this is kind of different from gas laws, where everything had to be in Kelvin. In heat calculations, if temperature becomes negative, we want to know that. Okay. Now you can do Kelvin in heat formula also, but in our book it focuses on using Celsius. Okay, so just know if you're ever given a problem they have Kelvin instead, it's okay as long as your specific heat is joules per grams Kelvin. Just make sure your units cancel, that's all you have to do, because a change in Kelvin and a change in Celsius is the same change because the increments of each degree is the same size. They're just kind of in different parts of the scale. Alright, so let's look at some examples. So it says the temperature of a 95.4 gram piece of copper. So again, a lot of you will read that and then for some reason you'll call this temperature. Well, it didn't tell us what the temperature is yet. It says the temperature of this thing. So 95.4 grams is a mass, so that's my M. Piece of copper increases from, whoops, that should say from, not form, typo, from 25 degrees Celsius to 48 degrees Celsius. So here are my temperatures. When the copper absorbs 849 joules of heat. So this is my Q, or my heat. Okay, so heat is going to be in joules. Then it says, what is the specific heat of copper? So I'm actually looking for C. I tell my students you can remember because specific has a C in it. So specific heat is C. Because a lot of you get mixed up between temperature, heat, and specific heat. So remember, temperature will be in degrees Celsius, or it could be in Kelvin. Heat will be in joules, it could be in kilojoules, and you may have to convert it. And specific heat will be joules per grams degrees Celsius or joules per grams degree Kelvin. I mean, not degrees, sorry, Kelvin has no degrees. Joules per grams Kelvin. All right, so that means I'm looking for C. Well, my formula is Q equals MC delta T. I am looking for C. So again, we divide by M and delta T to get C by itself. So I do that on both sides, so it cancels on this side. So C equals Q over M delta T. So then I'm just ready to plug in, since I labeled everything all nice and neat up here. So Q is 849 joules. My mass is 95.4 grams. And then my delta T. Delta T is not the same as T. Delta T is always your final minus your initial temperature. Always. Even if it means you're going to get a negative number. It's always final minus initial. So see, it went from this, so this would be T1 or T initial, to this. This would be T final. All right, so I do 48 minus 25. Okay, and then that gives me 23. And so this is my change in temperature. So this is what I plug in down here. Now, because I'm multiplying and have two numbers in the denominator, I will put that in parentheses to make sure my calculator gives me the right answer. And so a joule, a gram, and a degree Celsius will not cancel. So you do 849 divided by parentheses 95.4 times 23, close parentheses, hit the equal sign. It should give you about 0.39. And because none of my units cancel, I write all of them, joules over grams and degrees Celsius. Just like that. All right, and again, hopefully this is just a refresh from physical science, because you should have done this in physical science. If you took it, I guess you don't have to take it. You could have taken physics instead, and then either way, this should be super easy if you took physics. All right, so let's move on and look at another one. So if you're feeling confident, maybe go ahead and pause it and try this one on your own, and then we'll look at it together. So it says when 435 joules of heat, so remember joules is heat, but plus it told me it's heat, so that's my Q, is added to 3.4 grams of olive oil. So there's my mass, because grams is mass. At 21 degrees Celsius, so there's my initial temperature. The temperature increases to 85 degrees Celsius, so there's my final temperature. What is the specific heat? So remember, I see a C, so I'm looking for C. All right, so I'm going to have to rearrange the formula again. So Q equals MC delta T. I'm solving for C, so to get N and delta T on the other side, because currently they're being multiplied, I divide by both on both sides. So C equals Q divided by N and delta T. So now I'm ready to plug in. So my Q is 435 joules, because I've already labeled everything. My mass is 3.4 grams. And now I got to do that delta T. So remember, delta T is my final minus my initial. Even if it gives you a negative number, that's okay. It just means Q will be negative, and that means the reaction is releasing heat instead of absorbing it. All right, so my final was 85. My initial was 21. So once I subtract, I end up getting 69. And so I'll plug that in down here. So again, joules, grams, and degrees Celsius won't cancel. Since I have more than one number in my denominator, I'm going to put it in parentheses. And when you solve, you should get about 1.999999. So if you want to change it to 2, that's fine. And then I have joules over grams degrees Celsius, just like that. All right, so if you haven't tried one on your own, definitely try the next one because you really need to be able to do these on your own. Remember, it's one thing to watch me do them, but for you to do them on your own is totally different. Alright, so I'm going to assume you've paused it and tried this one. So it says how much heat, so this time I'm looking for Q, is required to raise the temperature of 250 grams of mercury, so there's my mass, 52 degrees Celsius. Now you may be thinking, wait a minute, there's only one temperature. Well, notice it didn't say raise it to 52 degrees Celsius where you would need to know what the starting amount was. It says raise the temperature 52 degrees Celsius. So in other words, they gave us the change in temperature. Alright, and then it says the specific heat of mercury, which is C, is my 0.14 joules per grams degree Celsius. Alright, so in this case, I'm solving for Q, so I don't even have to rearrange my formula. Q equals MC delta T, so I can just plug in. So my mass is 250 grams. My specific heat is 0.14 joules per grams degrees Celsius, and my temperature change is 52 degrees Celsius. Look, I don't know why I ended with a parentheses because I didn't start with one. Alright, so if you look, your grams will cancel, your degrees Celsius will cancel, and you'll be left with joules. So you just multiply your 3 numbers. And so I got 1,820, and then my unit is joules. Don't forget that unit. I'm super picky about units. Alright, so hopefully Q equals MC delta T wasn't that hard. It's just plugging in and doing basic algebra. And you get to use a calculator. So it can't get much easier than basic algebra with a calculator. Alright, so last thing that we have to talk about is the heating curve for a substance. In this case, I have the heating curve of water. So when you have a heating curve, across the bottom it's going to say something like amount of heat added, heat, sometimes it'll just say joules or something like that, kilojoules. And the y-axis of the side, you're going to have temperature. And then you're going to see a series of lines. So this is called the heating curve. So what we're doing is we're going to start with water at negative 10 degrees Celsius and go all the way up to maybe 120 degrees Celsius. All right, and so what this curve is showing is what's happening at each step. And so that's what you need to know, is what is happening at each step. I hope I'm like even on the camera at this point. I normally don't stand on this side. All right, so when we have water, if we are at negative 10 degrees, what state of matter are we in? We're in solid. So down here at negative 10 all the way up to 0, you see how it says H2O. That's saying we have solid ice right here. So what happens is at negative 10, as you add heat, it increases the temperature. That's why you see the line kind of going up. So it goes like negative 10, negative 9, negative 8, negative 7, negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, 0. Once it hits 0, what happens? Well, 0 is the freezing or melting point of ice or water. It just depends. Are you adding heat? In that case, it's the melting point. Or are you removing heat? In that case, it's the freezing point. So if you notice, once we hit 0 degrees, the line flattens. It doesn't go up anymore. What that means is the temperature is not changing at this point. But are we still adding heat? Yes, because look, we're still moving across and adding more heat. So how can we be adding heat and the temperature not change? Well, once you're going through a phase change, so see right here, it says you have some solid and some liquid because your solid's going to begin to melt. Once you start melting, the temperature remains the same until the end of the phase change. I know that's really, really hard to accept. I know it's hard to accept because when I was told this in physical science when I was in high school, I did not accept it. I was like, what? There's no way. You're heating it, so obviously it's getting warmer. Well, then we had to do this lab where we literally had a beaker of ice on a Bunsen burner, and we had to sit there and melt the ice and then heat it, boil the water. It was a super long, not exciting lab at all. So I'm not going to force my students to do that lab, but just accept it. Okay, so while you are heating it, if it is doing a phase change, temperature does not change. So then what is the heat doing at that point? Because it has to be doing something. Well, at that point, the heat is being used as energy to change the state of matter. Okay, so here When it's all a solid and we're changing the temperature, the heat is being used to make the particles move faster and have more kinetic energy, so temperature is increasing. Once you get to a phase change, the heat is energy being used to allow the substance to change from a solid to a liquid. So temperature does not change during a phase change. So at this first flat portion, that is when the substance is melting. But once all the solid has melted, if we continue adding heat, temperature will start increasing again. So here we have solid, we increase the temperature, it starts to melt. Temperature remains the same the whole time it's melting. Once it's done melting, the temperature can increase again. So now we have all liquid water. See, on this line, we have some liquid and some solid. You've all watched ice melt before. Okay, you get a little puddle of water and you still have some ice in there, and the puddle gets bigger, the ice gets smaller. Eventually, you have all liquid. So at that point, if you add more heat, you're going to start increasing temperature again. So here on this long line, we have water in its liquid form. So it's going to go, from 0 degrees to 5, 10, 15, 20, 40, 60, 80, and then it's going to hit 100. Well, what happens to water once it hits 100 degrees Celsius? Well, hopefully you already knew that's the boiling point. Okay, so here our liquid is going to begin to boil, and because that is a phase change, temperature does not change. Okay, so what I want you to notice is we have another flat line. So on a heating curve, your flat lines indicate your phase changes, because during a phase change, temperature does not change. I cannot stress that enough. All right, so it doesn't matter how fast or how much you heat it, you're just going to make it boil faster. It's still going to be at 100. All right, so what you have right here is you have some liquid and some gas, because some of it has started boiling. And so it stays at 100 until all of it has boiled. Now, if you had a way to capture the steam, so like we couldn't do this at our house, but in a laboratory setting you could. If you had some way to capture the steam, the gaseous water, the water vapor, then you could increase the temperature more. Okay, so once it all becomes a gas, then, I don't like how it says all liquid evaporated, because this is at the boiling point, so it should say all liquid boiled, but I didn't make this. So once all of it, they could have said vaporized, that would have been better, has become a gas, then you can add more heat and make the steam hotter than 100 degrees Celsius. Okay, so remember, in the parts that actually have a slope, that is when heat is being absorbed and it is making the particles move faster and temperature is actually changing. If you are at a flat portion of a heating curve, that is when a phase change is happening. Now, the last thing I want to point out is notice how short this line is compared to this line right here. The reason for that difference is think about the difference in what a solid and a liquid look like in like the molecular form. So like a solid, they're in their fixed locations and they're vibrating. In a liquid, they're still really close to one another, but they're flowing past one another. That's not a huge difference. We have real close together and vibrating, or real close together and flowing. So it doesn't take a huge amount of heat to change from the solid to liquid form. Now let's think about the difference in a liquid and a gas, and we'll realize why that line's a lot longer, why it took a lot more heat to boil it. Well, in a liquid, we have particles really close together and they're flowing. In a gas, we have particles really, really far apart. So we have to take the particles away from one another. That's what takes that extra energy. So if you were asked a question about, which one would need more heat or more energy added, it would be the boiling, because you're trying to take the particles apart. You're you're breaking all those intermolecular forces between them. All right, so that is a heating curve. There are math calculations that go along with it, but we only do those in honors. All right, so hopefully thermochemistry wasn't too much for you to handle. And hopefully you remember that Q equals MC delta T calculation from physical science.